So you now know quite a bit about the Sharpie impact testing machine and the Sharpie or the IZOD type of specimens that we can break for impact testing. And here we are just saying that knowing the mass of the pendulum, the difference between its initial and final heights, the energy absorbed by the specimen until fracture is measured. On the next page, what we are showing you is very important. Let us see. What do you see on the vertical axis? The energy absorbed. So this is the Sharpie impact energy, and horizontal axis, temperature. So remember, when we were talking of ductile to brittle, ductile materials and brittle materials, we were also talking of something like this. So every material, there is an effect of temperature on the properties of the material. You know, right? If you heat something, it becomes soft. If it becomes very cold, it becomes a little harder, and so on. So now we have measured here, say, in this diagram, the Sharpie impact energies or the impact toughness of different materials. These are FCC metals. When we will go back to the chapter on crystal structure, we will see that face-centered cubic is one type of crystal structures. So these are that type of metals which have FCC crystal structure, and if you see, they have a lot of impact energy. So they are tough, they are good on toughness. Here we have high strength alloys, metal alloys which are very high in strength, but their toughness is low. So this is unfortunately a regular thing. We have talked a bit earlier that if a material is very strong, generally its toughness will be a little low. So these are those materials. This black one, they are interesting. These are low strength metals, medium strength metals, and BCC is another structure, body centered cubic crystal structure. Like normal low carbon steels and so on, they are all BCC metals. So these type of metals are medium strength, and if the temperature is reasonable, right, 20, 25, 30 Celsius and so on, then they have good impact strength. But if you reduce the temperature and go to near freezing temperature, for example, their impact strength drops down a lot, and now they have a very low impact strength materials like glass and very brittle materials. So this behavior, that at normal temperatures they have good toughness, they have good ductility. At low temperatures near freezing and below, they become very brittle with very low toughness. So that is why it is called ductile to brittle transition, and the temperature at which this happens is called the ductile to brittle transition temperature. So this is a major problem, and earlier, say 100 years ago, engineering was already very good. They could make cars and trains and all those things and big ships, but they did not know that there are some metals which are reasonably good in their strength and hardness and ductility and so on, but they will go through change in the toughness, right? So we are showing it here because these values are the toughness values. These values are the toughness values. If the toughness is high, the material is ductile. If the toughness is low, the material is more brittle. So these are by nature good ductile metals. These are by nature ductile but not as good, and these are the change in nature materials which are ductile at some temperatures with good toughness and brittle at some temperatures with another lower temperature. So with this, we finished this second part, right? We were doing the tensile testing, and now in the last few slides we have talked of the impact testing and how it is used to measure toughness of a material. We now go to the third test, mechanical test, hardness and hardness testing. Again, don't read now, don't read, because this is one question which I always like to ask you. I don't remember if I have asked you in a previous slide or not, but maybe I have. So if I ask you now, don't read, right? Don't read at all. If I ask you that, tell me one sentence of what is hardness. Tell me one sentence about what is the strength. Whether it is yield strength or ultimate tensile strength, it is the strength of the metal. So if you have to explain to a child, or if you have to explain to a student of Thanviya that metals are there, what is a strength of a metal? Say one sentence, right? So think on it. Pause my slide. Think that give us a one sentence very good definition of what is a strength. So if you have the correct answer, a very good answer would be resistance to permanent or plastic deformation. This is a strength. Or in general, resistance to deformation. If a material has high yield strength, you will have to apply a lot of force before it can deform plastically, isn't it? If a material has high tensile strength, you will have to do a lot of force before it can fracture. So whether it plastically deforms, permanently deforms, or ultimately it fractures, you don't want to do that. The resistance to this is a strength. Resistance to permanent plastic deformation. Now, without reading again, try to define in one simple English language sentence hardness. What do you think hardness is? Think. Now some of you are saying again resistance to deformation. Is it right or wrong? Is hardness the same as a strength? Right? So it is confusing. So no, those who were saying that hardness is also resistance to permanent deformation, they are not wrong. It is correct. But then what is the difference between a strength and hardness? So yes, they are very similar. First thing, they are very similar. If strength is high, hardness will also be high. If strength is low, hardness will also be low. But they are not exactly the same. So the problem is in the books also, when we define hardness, many times they say it is the resistance to permanent plastic deformation. But now again, without reading, let me tell you something. Take a piece of metal, right? Take a piece of metal. Take a piece of glass. Take a piece of butter. Just butter, a block of butter that you eat, right? Now take a knife. With the knife, on the surface of the butter, try to draw a line. With very little force, you will make a line. Now try to draw a line on the surface of glass. With that force which you used on butter, you can't scratch it. But you try harder and harder, and after a little time, you will be able to put a mark on the surface of glass. Now take the same knife and go to steel and try to do it. You will not be able to put a mark on the surface with the same force that you did for the glass. You will have to put a much larger force, and only then you may be able to scratch it. So so when you put a line on the surface or when you put a scratch, you are deforming it, and you have permanently deformed it. That scratch is there. It is not that when you remove the knife, the mark is gone, right? So it is not elastic deformation. It is a plastic deformation. So you needed very little force to do that for butter, then some more force to do that on glass, and some more force to do that on steel. So this is resistance to permanent deformation, but we are applying it only on the surface. We are not trying to deform the whole body. So now, right, so now you can modify that hardness is the resistance to permanent plastic deformation on the surface. On the surface, only on the surface. You do not try to bend the whole piece. You do not try to break the whole piece. You just want to make a permanent mark on the surface. This, you know, when your car has a small accident, you say that there is a dent in the body, D-E-N-T, dent, and you go to a shop, denting shop, and they remove the dent, right? So the surface has changed a little. So this is a dent, and to make a dent, it is called indent, I-N-D-E-T, indent, indentation. So the best definition, rather than a long one of hard, because indent means to make a mark on the surface. To indent means to make a mark on the surface. So hardness is a resistance to indentation. That's it. If you say this and the person understands what is indentation, then the meaning is totally clear. Hardness is the resistance to indentation. But long one, hardness is the resistance to permanent deformation on the surface. So this was the definition. Now you can, hardness is a measure of the resistance of a metal to permanent plastic deformation on the surface only, right? So therefore I have written resistance to indentation. Now, how do you measure hardness? You see, how do you measure tensile properties? You take it to a tensile test. How do you measure impact toughness? You take it to an impact testing machine. So how do you measure hardness? You take it to a hardness testing machine. But what will a hardness testing machine do? It will try to apply some force only on the surface and see if there is a permanent mark there or not. If you apply a force, remove it, and there is no permanent mark, then you can't measure hardness. It was only elastic deformation. So you apply enough force on the surface so that you can indent it. You can make a small dent on the surface, and then by measuring how much force you applied and how much dent you made, then you can measure the hardness of the machine. So this is why what we are saying here, this is the machine, any machine. Press the indenter that is harder than the metal into the metal surface. Withdraw the indenter. Measure the hardness by measuring the depth or the width of the indentation. Right? So this is the method. This is the method. We will just show you the machines. But right, so the machine is such, it is a simpler machine than the others, but it will press something into the metal. And of course, as we have just showed you, here, if the material of the machine would be harder than the machine material you are testing, otherwise you can't change it. So here we are showing you that, you see, for example, there is a sphere, there is a ball, there is a sphere, there is a ball. You apply a force of a known amount and you know the diameter of the ball. Then you remove it. Once you remove it, it has made some indentation. Measure the dia of the indentation, that is the small d. So this capital D is the dia of the original ball. You know the amount of force with which you applied it and kept it here for some time. Then once you removed it, it left a small dia, small d. And by measuring this force and this small dia d that we had, and knowing what was the dia of the original size, then we can calculate the hardness of the machine. This is hardness, right? So hardness is the resistance to permanently indenting the surface, and large hardness means large resistance to plastic deformation, right? And better wear properties. The word wear, W-E-A-R, wear, is very important in engineering. What is wear? You see, in normal English, you say, I am wearing a shirt. I am wearing a shirt, right? I am wearing a dishdash. But when in engineering, two pieces are rubbing against each other, they are rubbing against each other, then after some time, the surface will not be good. The surface was originally very nice and good, but if they keep rubbing against each other, after some time, there is some small roughness created on the surface. So if the roughness created on the surface is because of friction, because of rubbing against each other, then this is called wear. So we need wear resistance in materials. We don't want their surface to go back. For example, inside the engine of a car, there is a piston cylinder system, right? There is a cylinder and a piston, and there is an up and down, up and down, up and down movement. So there is a lot of friction, and we don't want any wear on the surface of either the piston or the cylinder, so that the engine works well. So any material which has high hardness will have a resistance to deformation and will have a resistance to wear. So this is a very good property for high hardness, that if the hardness is good, then the wear resistance of the material is also good.